Welcome to That Science Tutor. In this video, we're going to take a look at 10 exercises from series and the sigma notation. If you don't know what the sigma notation is, check out my other videos, but just to recap, it's this Greek letter that in essence means just summing. So we will basically add up all these terms in different series. Our first exercise says write the series in full. Our first example runs from 1 to 4, which means we start by substituting r for 1 for our first term. So our first term is actually just 2 times 1 times 1 minus 1 in parentheses. This is 0, so we get our first term is 0. Since we said it's summing, we just add a little plus and go with our next term, substituting r for 2. So we get 2 times 2 times 1 minus 2. This is minus 1, so we get 4 times minus 1. This is minus 4. Our third term is just substituting r for 3, so we get 2 times 3 times 1 minus 3. This is minus 2, so we get 6 times minus 2, which is minus 12, which is also our third term. And then our last and fourth term, we just substitute 4 instead of r, and we get 2 times 4 times 1 minus 4. This is minus 3, so we get 8 times minus 3, which is 20, minus 24. And we can just write these terms down a bit more nicely. So we get 0 minus 4 minus 12 minus 24. You can go ahead and calculate, but it's not necessary. So we are going to take a look at example 2. We start from 0 and go to 5. So basically our first term is minus 1 to the power of 0, which is just 1. So minus 1 to the power of 0 times 0 squared. 0 squared is still 0, so this is 0. Our 0, or first term for r is 0, is just that. And then we go and substitute in 1 for r. We get minus 1 to the power of 1 times 1 squared, which is minus 1. So we do the same with the next term, minus 1 to the power of 2 times 2 squared, which is 1 times 4, and that's 4 plus 4. Our fourth term is minus 1 to the power of 3 times 3 squared, which is minus 1 times 9, and that's minus 9. We see now this, and then substituting 4 instead of r, we get minus 1 times 4 times 4 squared, which is, this makes 1, this is 16, so we just get 16. And then our last term, the sixth term, substituting r for 5, we get minus y 1 to the power of 5 times 5 squared. This is just minus 1 times 25, which is minus 25. And we can rewrite this with all the minuses, so we get 0 minus 1 plus 4 minus 9 plus 16 minus 25. We're now gonna take a look at the third example, which is a bit different. We don't have any r's to substitute in, but we can actually do something. We can rewrite this, basically this 5, just as 5 times 1, because we know that anything times 1 is the same number, so we can get 5 times 1, and we can rewrite this 1 as r to the power of 0, because anything except 0 to the power of 0 is 1, and we see that we start with the term r is 1, thus it will make sense. So we basically do just that. 5 times the power of 5 times r to the power of 0, and now we just go ahead and substitute, and we get 5 times 1 to the power of 0, which is still 5, plus 5 to the power of 5 times 2 to the power of 0, which is still 5, and then 5 times 3 to the power of 0, which is again 5, and 5 times 4 to the power of 0, which is once again 5. So we basically get 20, but that is all the terms of this sequence, even though we had no r previously written. So be sure to do something like that if you ever encounter a problem without an r, but just with numbers. So it's something similar here. We are writing the first 5 terms of the series, so these are called infinite series because we see that we sum all the terms from 1 to infinity. So our job is just to write the first 5 of them, which is basically the same as writing r is running from 1 to 5. So let's see. Our first term here is going to be minus 1 to the power of 1 over 2 times 1 squared minus 1, which is minus 1 over 1, which is basically minus 1. Just to keep that in mind, I will write that here. Okay. Our second term is minus 1 squared over 2 times 2 squared, which is 4, minus 1, so we get 1 over 8 minus 1 is 7. I will write that here. And then our third term, just substituting these numbers in, is minus 1 to the power of 3, which is minus 1. In the denominator, we have 2 times 3 squared minus 1, which is 2 times 9, which is 18, minus 1 is 17, so we get minus 1 over 17. And then we have our fourth term. We just substitute 4 in, so basically minus 1 to the power of 4 over 2 times 4 squared, which is 2 times 16, minus 1. That just brings us to 1 over 31, which is our fourth term, plus 1 over 31. And for our fifth and last term, we get minus 1 to the power of 5 over 2 times 5 squared minus 1. So we get minus 1 over 2 times 25, which is 50, minus 1 is 49. And that is our last term. I'm gonna just rewrite this a bit more nicely. And we get minus 1 plus 1 over 7 minus 1 over 17 plus 1 over 31 minus 1 over 49. Okay, and then we have the last example in this exercise. So we get r to the power of r, while r is running from 1 to the infinity. Okay, so basically our first term is 1 to the power of 1 plus 2 to the power of 2 plus 3 to the power of 3 plus 4 to the power of 4, and for our fifth term 5 to the power of 5. So if I just write this a bit with numbers, we get 1 plus 4 plus 27 plus 256 plus 3125. So we will now solve the third exercise, which requires us to write this series with the sigma notation. So let's go and see the example 1. So I can see that the first term is for 3 bigger than the next one, and again the second term is for 3 bigger than the third one, and so on. So I can see that this pattern is continuous, and I could say that the common difference between the terms is minus 3. And I just now need to write this down as using the sigma notation, and it's easily done. I will write it as 8 minus 3 times r, because we can see that the number of r's we decreased the number of 8 by increases with every term. And I just write the sigma notation here, and now I decide about the bounds. And I can see that if I put the sigma notation running from 1 to some number, my first term is going to be 8 minus 3, which is already 5. So I can just do a little trick and say that it's running from 0 to, since we have 5 terms and starting by 0, I will just write 4. And while this certainly is the correct answer, there is nothing wrong with another answer, which would be 11 minus 3 times r, and the sigma notation running from 1 to 5, because we can see that the first term would be 11 minus 3, which is 8. So basically we get the same sequence, the only thing we changed were the bounds of the summation. Now we will solve the second example, and we can see something. The difference between the terms is not continuous. So first one goes up for 7, then for 11, then for 15, and then for 19. Well, we won't be able to just write one number for the difference because it's not continuous. We can see something. So I can write 3 simply as 1 times 3, then as 2 times 5, 21 as 3 times 7, 36 as 4 times 9, and 55 as 5 times 11. So I can see that the first number in this multiplication increases by 1, and that's something I wanted, r changing for 1. So I will write this series simply as r, and that's my first point, but I need to multiply it by some other number, preferably integer, to get to this series. And we can see all these integers are odd, and how we can usually write odd integers is by 2k plus 1, well, specifying that k is an integer, but I can just write 2k plus 1 as an odd number, in this case as 2r plus 1. So we are multiplicating 1 by 2 times 1 plus 1, which is 3, and we get the same equation as I wrote below. And then for the second term we get 2 times 4 plus 1, which is 5, is 10, and that's exactly what I wanted. So I will just rewrite that sigma notation below this equation, and we get r times 2 times r plus 1 in parentheses, and I just write the sigma notation running from 1 to, since we have 5 terms, to 5. And that's also the solution to this example. Then we have another interesting example, and what I need to see here is that it actually all increases very steadily, because I will rewrite 1/2 as 2 over 4, and here I have 2 over 3, and I will write this as 4 over 6, and then we have 0, but 0 can be very easily written as 0 over 2, and then I see that my numerator increases every time by 1, so 0, 1, 2, 3, 4, 5, and my denominator increases also by 1, so I have 2 plus 1 is 3, 4, 5, 6, 7. So my term now and my sigma notation is just r, which is increasing by 1, over r, which is also increasing by 1. But I need to see that here I have 0 and I have 2 for the same number, for the same term r I'm going to put in. So for my first term I need to get 0 in the denominator and in the numerator, so I will just put 1 minus 1, which is 0, and in the numerator I have 1 plus 1, which is 2. So that's my sigma notation for this series, and it's running from r is 1 to, since we have these 3 dots, it just means infinity. And that's also the solution to this exercise. Our next example is this fourth one, which is basically just a sum of squares of odd integers. We can see this as 1 over 1, 3 over 2, and 5 over 2, 7 over 2, and 9 over 2. And we can see that these are basically just odd integers. And I said we can write odd integers as 2k plus 1. And that's basically it for this example. We just write 2k, instead of k we're gonna use r, plus 1 squared, and we just said since we used r, we will also use r for the sigma notation, but in case you wrote that one down, you can just use k is running from certain number to the second certain number, and we can see that if we put the sigma notation running from 1 to 5, since we have 5 terms, we see that our first term in that case would be 2 times 1 plus 1, which is 3 squared, and we would get 9. So we need to figure out that for such expression we need to set the sigma notation running from 0 to 4. However, there's also another solution to this problem, and that would be writing down odd integers as, I will write this time 2k minus 1. We can see that this also represents odd integers, and we can say in such case that the sigma notation is running from k is 1 to 5, as we can see that the first term would be 2 times 1, which is 2 minus 1, and that's 1 squared. And that's our first term. So those are both correct solutions for this example. For our last example of the day, we have just 3 times k plus 6 times k. We can see that we are multiplying 3 times certain value, in this case 1 times k. We have then 3 times 2 times k, and then 3 times k, and so on. So we can see that in our expressions we have integers that are increasing by 1, and that's exactly what we want. So we can write these as r, because it's increasing by 1. So we just write 3 times r times k, because we have k in the expression, in the series, and it doesn't specify what k is, so we just have to leave it there, and we just write our sigma notation, and we will specify that r is running from 1 to, since we have 5 terms, to 5, and leave the k there as it is because it's not specified. And that's basically it. We've solved all the examples of series and sigma notation. If you have any more questions, please leave them down in the comments and I will turn to you as soon as possible.